maybe I don't know whether there is some structure to ask question. If people have any question, you can ask. This should be more interactive session. So,
Actually, this meeting is kind of webinar one way, but they will write their question on chat actually.
okay, sir.
We'll manually unmute them. Thank you.
Okay, so I find how the chat one. Okay, so maybe I'll go ahead and then later on we can look at the chat. So now look at the so this is one of the study conducted by Intel many years ago. It's bit dated, but the trends are the same. So what did they studied is that how much cost it incurs when they design and manufacture a transistor, and how much cost it incurs when you are testing that particular transistor. And initially, in say 80s or 90s, when the designs were small, there was big difference between the cost of testing and cost of design plus manufacturing. However, by the 2020 or so, this cost of the design plus manufacturing almost became equal to, because the cost of the design plus manufacturing both were reducing, and now the cost became almost same. And now, I mean, it was supposed to cross the test cost was supposed to cross over the design plus manufacturing cost sometimes around 2020. However, they are still, they have not crossed, but they are still close to each other. That means if it crosses, that means the cost of a device would be determined by the test cost, not determined by the manufacturing and design cost. Even if it is similar, in that case this is a significant part. So like here, say for example, if you buy a device in 400 rupees, that means here 200 rupees have gone in the design plus manufacturing, and 200 rupees have gone in the test of the device. So the test is that expensive today. And therefore, now if I look at this, see, the design and manufacturing cost is going down and down every year, whereas you see that there is a almost flat curve that we have uh, in terms of the test. There was a little dip around something 1990 or so, but after that it is more or less the similar flat curve. Does it mean that here the test engineers have or test researchers have not done enough? That's how this is staying constant. It's not that test engineer have not done anything or test researchers have not done much work, but the every say you see that here the technology roadmap says that the number of transistors will double every 18 months. Now, if the number of transistors are doubling every 18 months, uh, mean that I have the design with the larger complexity, and in order to deal with that, here we have to put more effort. So the I mean, like Moore's law that says that the number of transistors will double every 18 months. In the similar way, there is a law for a test vector, that the number of vectors will double by every 10 months. So that is even faster than the number of transistors that those are doubling. And therefore now I mean, keeping it constant itself is a big humongous task. So if we can confine that we within that constant range, so that means that the large responsibility goes to the VLSI test engineers to keep the test cost as minimum as possible, so that your chip, because now the chip cost is almost like determined by the test cost of the chip. So and I'll give you some number, uh, that how expensive it is. So now there are, I mean, there is a whole lot of say innovation in the design, but with the innovation in the design, this comes with many new things, like the power consumption of a device has been increased tremendously. And so this was like the projections that people had earlier, that if you would have gone through the same design methodology and the manufacturing technology, perhaps the power consumption of a chip might have gone to the power consumption of a rocket nozzle, which is very difficult. So that, I mean, that says that we have constraint, we are not increasing the frequency of the design, so that we can, you can constrain the power dissipation. Similar way, the leakage power in the memory, etc., is or even in the circuit is increasing, and that put the additional constraint while we are testing the devices. The third thing is that the activity inside the chip doesn't remain uniform. Those are non-uniform, and then some area is heated more than the other area. That also comes along with the different constraints when you are not only the designing the chip, but then when you are testing the chip as well. So now here, if I say the VLSI testing, in that case, the main focus of VLSI testing is, and the challenges that we are getting is, we have I mean, the circuits that we are manufacturing, they they come with the defect. And now now if I look at the high-end circuits, high-end circuits are mostly the microprocessors, which are say designed at the cutting edge. So those kind of circuits have yield something like here 20% to 50-60%. Now, if I say 20% yield, that means 20% parts are the defect-free parts and 80% parts are defective parts. And you have to weed out all the defective parts from the lot of or the manufactured parts that you have. And now, because 20% parts are only the useful parts that you can ship to the customer, therefore you are getting revenue from those 20% parts, and therefore the per part cost may go 5 times than the comparison to the case wherein you have all parts which you are manufacturing are say non-defective parts. So those are the big concern of VLSI test engineers, that how to ensure the parts which are likely to be more defective, that the no defective part will go to the customer. That's the main thing. Say for example, you want to get you want a chip that you are using in the braking system of a car, and so in that case, now you say, I mean, we are manufacturing, and say 20% chips are good, and 80% chips are bad. Now you cannot afford to ship a bad chip, a single bad chip to the customer who can use that in the braking system. And then maybe the test engineer who can test can say that here, oh, I mean, I can tell you that with 99% confidence this chip will work, but 1% case I cannot say that here it will work or not. In that case, nobody would like to ride in that particular car wherein somebody says that, oh, 99% it will work, but 1% it may not work. So what you want the 100% confidence, and therefore you have to have a sophisticated mechanism to weed out all the bad parts that we are manufacturing. So ICs must be carefully tested to screen out all the faulty parts before integration in the system. As you go higher and higher, say, level of the system design, maybe from the bare chip that you have manufactured to the say chip which is packaged to the integration on the board to the integration into the system. As you move up in the ladder, and if you find the chip as a defective chip, in that case the cost it incurs perhaps may increase 10 times every time whenever you are going on the higher in this ladder. So the latent faults that cause early, so it is not only the faults when the parts which are defective that you want to weed out, but you also want to weed out those parts which are not defective today, but they are weak parts. For example, if I say draw a line to connect 2 points in the system, and that line may not be the uniform line. Somewhere the line is thin, somewhere the line is thick, and when it is thin line and the large current flow through that, it will heat more, and after a while the metal may evaporate, and you may get the open out of it. So those are the parts which are not faulty parts today, but they may fail in the system when it will operate, maybe after 3 months or after 6 months or after 1 year or so. So you also want to weed out those kind of parts that we should not ship to the customer because they are likely to fail in near future. And for that we go through something called as burn in test, that is even much more expensive. Maybe if time permits, some other day we will discuss what is a burn in test. The burn in test is a big say issue in the industry, how to do the burn in, because it is very expensive as well as it is not that effective today. And what are the challenges, maybe I will discuss in some another day. So now the main aim is to test the chip, and then to test the chip we have to develop the test set which can help you in testing the chip. So in chip testing, what is the main aim that we have is that whatever chip we have manufactured should work as per the specifications. Now, this chip testing is, I mean, so when you manufacture and when you design a chip, develop the GDS2, and then go to a foundry. Foundry people will invariably ask you that here how you will test that particular chip. So this is a typical conversation that goes on between a designer or design house and manufacturing fab. So for example, you go to the TSMC and say that here I want to manufacture this particular design. My design is complete. I have checked, I have verified my design all through. It works correctly. And now I want to get it manufactured. Now, fab vendor says that how will you test this particular device? Maybe you can say that I have checked that my design is correct. That means there is no bug, and I know how to test that particular device, what I need to apply, and what I want to check. But then again, fab vendor says that here you have checked your design thoroughly, but at the end, how will you test? So maybe design house may say that here why that is important for you. It is my chip. I mean I will find my way. I will test this. So it is you can say that here you manufacture it. It is between me and my client. This is none of your business that how I would test. Maybe fab vendor can say you that sorry, uh, you can take your business somewhere else. I don't want to manufacture. So that's the so that means now this you have to go to the another vendor. The same thing will happen there. So that means you have to have you have to tell them a way that here how will you test that particular device without say telling them that how you will test. They won't manufacture your design, your device. Why that is important? Because now tomorrow when they will manufacture, you will say some device doesn't work, and you may say that this is your fault because you didn't say fabricate correctly, or device people will say that here this was your fault because your say layout was not correct, and so on and so forth. This blame game may keep on going. So therefore you have to tell them that these are the test vectors. I want that my design should say pass these particular test vectors. Now those tests, what this should have, my test must be comprehensive. So that means here it should give me the full confidence on my device that this design has been correctly manufactured on on the silicon chip. And it must not be too long. That is very important. I'll come to this point, why this is so important. Because I need an expensive tester to test that particular chip. When you need an expensive tester, mean what? Say for example, maybe I'll discuss later. I buy a tester, and then tester I will use for next couple of years. A tester which is designed particularly for to test the chips is quite expensive, cost you billions of dollars. And then if you spread that cost over the say per unit time, you will find that the cost of test per unit time is almost like a 5-6 rupees per second. 5-6 rupees per second means if I want to test my chip for 1 minute, it should cost me 5 into 60, that means about 300 rupees, right? So if you test for 1 minute, it will cost you 300 rupees. So therefore now even you cannot afford to test a device in a minute. Your device has to be tested within few seconds to few minutes, forget about hours. So that means the kind of test vector set that you have, that you use to test, should not be too long, should be applicable within few seconds to few minutes. That's the kind of thing that I need. So there are issues in this. Now you have to model the possible defects that can happen, because you can, I mean, I'll come to this point that you cannot test it functionally. And if you cannot test the functionally, in that case you have to model that what kind of defects I'm likely to get in when I'm manufacturing the chip, and then test for those defects. Develop some kind of logic simulators or fault simulators which can help me in designing such kind of test vector. And develop a test generator. That technology you will be say learning in say some time. So then the some methods to quantify the test efficiency, how good your test method is. So now the need for testing would be to check, to make sure that your design that you have manufactured is providing you the correct functionality. The if the density in the chip of the devices is higher, in that case you get the higher probability of failure. So you can estimate that what is the probability of failure that I'm going to get. The For the life critical applications, you want to, you are more aware. So that means you have to pay more, more, I mean, you have to treat the designs which are for different kind of applications. For example, if the chip that I am using for the audio entertainment device, and then chip that we are using for the braking system that we are using in automobile, have to have very different requirement, because in audio system, if something doesn't work, and then like one particular sample is not processed, perhaps you may not be able to even recognize. However, if you apply a brake, and then if that brake doesn't work, in that case that can result into a catastrophe. So therefore then we have very different requirement for the different applications. And now ultimately, what say determine that how elaborate my test is, that is governed by the cost of the test, that govern the entire business. Now, what does the testing achieve? Testing, just the aim of testing is to discard the bad devices, and then use the new ship the good devices. So if I can say compare the verification and test, look at this little bit carefully, because often people say confuse between the verification and test. What is the verification and what is the test? Verification verifies the correctness of the design, the software design that you have created, whether that design is correct or incorrect. So this verification process will verify whether your design has any bug or not, it is correct or not. However, test verifies the correctness of manufactured hardware, that whatever gate level netlist I have designed, whether that gate level netlist has been implemented or fabricated on the chip or not. So we are say want to find out whether that particular say the layout has been implemented, or there is a manufacturing defect in that. Verification is performed by simulation or hardware emulation, or by some formal verification. However, test has two phases. One phase is to generate a set of vectors that you have to apply onto the chip. So this process is a software process, something like a verification you need to do once in your design cycle. However, each and every device has to be tested, and therefore these test vectors have to be electrically applied on each and every the manufactured hardware. So that is like a recurring cost. If you are producing billion chips, in that case all billion chips have to be tested. Verification is the process that is performed once in the design cycle. So once you verify the design, you send to the fabrication house, and then fabrication house will say fabricate multiple devices. In test, the test has to be applied or performed on each and every manufactured device. So this is the difference. Verification is only once, test has to be applied on each and every manufactured device. Verification is responsible to ensure the quality of the design. However, the test is responsible to ensure the quality of the hardware devices that we are producing. So this is the difference between the verification and test. Often keep in mind, often people do confuse between these two terms. So the problems that we have with the ideal test is, ideal test is supposed to detect all the defects that can happen in the manufacturing during the manufacturing process. Now, all defects, I don't know, maybe I'll discuss these things in a few minutes time. But then there can be numerous defects that can happen. Maybe there can be open in a line, or the two lines can show to each other. Maybe say uh, the say the gate maybe be sorted to the substrate, or something like that. The any such kind of defect can happen. Ideal test should pass all the functionally good devices, and it should fail all the bad devices that we are producing. These defects are very large in number, and they are variety in number. There can be many kind of defects that can happen. And those perhaps we may need to test. So now it's very difficult to generate the test for a real defect. A defect oriented testing is still open problem. Anybody, if is interested, this is a very difficult problem to crack, to develop a methodology to generate the test targeting a particular defect. So now these are the ideal test. Now in real test, what do? We have to, we cannot detect or cannot develop the test for each and every possible defect. Rather, we make a model of the defects, that how defects manifest itself in terms of logical malfunctioning of the chip, that we call as a fault. So now we make a model of the defects that can manifest itself as a fault, or the incorrect operation. Until unless a defect result into incorrect operation, I don't need to worry about that. So you have to be like a look at that, or we develop the fault models which can map, or match the real defect in the design. We may get the incomplete coverage of the modeled fault. So now here we are modeling the way the defects are occurring in the system, and those the modeled faults that we have, perhaps because of high complexity, we may not be able to test for each and every modeled fault. And if we cannot, in that case there is a reduction in the coverage, and wherever we are not able to test the modeled fault, we are not sure that whether that fault is there in the manufactured circuit or not. If it is if it is not there in the manufactured circuit, perhaps it is fine. But if it is there in the manufactured system, in that case I have no way to test that particular defect, and then it will go unnoticed, and somewhere somebody will realize that he or she is getting the wrong result, and then at the end they will send back the chip. So that means now here, some of the because if it is not the complete coverage, some of the good chips are rejected, and then some of the bad chips can pass. Now if good chips are rejected, in that case you may be able to sell less number of chips, and therefore there is a yield loss of the system. However, if the bad chips, because of your bad process, if they are slipping through and then can go to the market, in that case, that because those defects would be uncovered after a while when chip is operating in the market, and they will send you back, and that will increase something called as defect level. Defect level is defined as how many faulty chips you are sending to the market over the total number of chips that you are say selling. So this chip is like here, so process is something like that. You have some chips which are good chips, some chips which are defective chips or bad chips. And then now what you want that here good chips should be identified as good chip, and bad chips should be identified as bad chip. However, some of the good chips can be because of inadequate test, the some of the good chips are identified as bad chips, and that we call as the yield loss. Or some of the bad chips can be classified as good chips, and that will increase the defect level. The process is pretty much like here the examination process. So, like for example, if I teach a course for 6 months, and in this total course, Perhaps there may be numerous questions that one can construct. Maybe say one lakh questions one can construct. Now I can only be sure that whether students are learning everything or not if they can answer all the questions. Now if I give an exam that has 1 lakh questions, perhaps it may take 1 year for for any student who is taking the course to answer, and which is not feasible, right? That for one course that I taught for 6 months, and then you spend 1 year to answer the question, and after that I can tell that, oh yeah, whether you are the pass quality student or a fail quality students. So let's say, for example, in a class there are 75% students who are good, they are pass quality student. 25% students, perhaps all students who are coming are good, but then perhaps they may not be that sincere, they may get some mishappening or something, and then they are became of fail quality. Now out of the 75%, if I say that it identifies most of the students, pass quality student, as the pass quality students. But some and all this happens because I cannot do the exhaustive testing. What we do is, when you are tested, you are given with a 3 hours exam. In 3 hours exam, out of 1 lakh questions, I can ask only 15-20 questions. Now based on 15-20 questions, we want to identify a student, whether a student is a pass quality or fail quality. Because of that, this may possible that all pass quality students can, because they have studied the entire syllabus, can answer those questions. However, there are some students who perhaps may not have studied that portion of the course, and may fail the exam. And that means those students are good, they have good knowledge, but then because of the exam paper, 3 hours exam paper that I set, perhaps that portion they did not study, and they are failing that. On the contrary, that the students who are fail quality students, perhaps the question paper should be designed in such a way that most of the students will fail in that question paper. But you may find that some student who never studied during the semester, but in last night they studied some questions, and they find similar kind of questions in the exam, and can pass. So those are the students who are really do not have much idea about the course, but they somehow studied some portion in last night, and can answer those questions and pass the course. Now this is a big dilemma in front of a examiner, that what kind of question paper he or she should set. So that idea is that all the pass quality students should pass, all the fail quality students should fail. Now if I become too strict on that, then all fail quality students will fail. However, some pass quality students also may fail. That is the so that we call as risk of students, that some good students may also fail. So that is like a yield loss in the manufacturing sector. On the contrary, if I set question paper bit easier, in that case, maybe all pass quality students will pass, but then some of the fail quality students perhaps may have studied last night that portion, and then can also answer those questions and can pass. So in that case, now there is a, this is we call as teacher's risk, because now there is a risk that the teacher is passing those some of the students who are not really the pass quality student, but we are passing. So because of say this 3 hours exam, or a short exam, we have all these problems. Similar kind of problems are there in testing the chip, because I want to test. Only the difference is that in the exam test, we can pass students if they are getting something like a 40% or 50% marks. So that means your 40%, 50% answers they have made correct. In that case, we are passing. However, in chip, you cannot take this say a risk. You chip has to pass all the possible tests that you have. Now the challenge is how to construct the say the test vectors which can give you the reasonably the same confidence that you are getting out of the exhaustive testing of the chip, that you can apply in long time. However, because we cannot apply all possible vectors, you can apply only a few vectors, and therefore some chips may be shipped as a bad chip. So now the testing has several roles. One role is to detect whether device is faulty or fault free. In general, when we are saying VLSI test, in that case, our aim is to detect whether device is faulty or fault free. If it is a faulty device, you have to throw out. You don't need to worry about that what defect it has. But if multiple devices are failing, in that case there is something systematically wrong with your designs, and therefore you have to diagnose that those devices. So diagnosis means your identification of a specific fault that is present in a given design under test. This can be used for the failure mode analysis. Failure mode analysis means here what went wrong in the process, because of that you are getting so many defects in the finally manufactured design. So in test, I have, I mean, we can test the chip at the different level. So you have a design, the design has to be say you have specifications that has to be synthesized, and then synthesized design has to go for fabrication. After fabrication, you package the device, and then you have to do the quality assurance. So now first you have to test the design. When you have various say chips fabricated on a wafer, once you have completed that, and after that you have to test after manufacturing, and then you have to test after say packaging for the quality assurance purposes. Now, how difficult this exercise is? Let's take this example, that if I have a NAND gate, in order to test this NAND gate completely, what I need, there are 3 inputs and 1 output. So 3 input NAND gate, how many inputs we can apply to this? 3 inputs means it can start from 000 and can go all the way to 111. So therefore we can apply 8 inputs, and then we can check against the truth table of this NAND gate. If there is a match in the truth table, I can say that this NAND gate is manufactured correctly. Now, if there is a defect, in that case, it may not give you the correct output. And therefore, what you need to do is you have to apply the we so um, so now I need to apply 8 inputs to completely characterize whether this NAND gate is correctly implemented or not. That is the case when I have only a small number of inputs, 2 input. But in a real design, you have large number of inputs. Like here, for example, if I use a 64-bit adder, those are quite common in your computing chips. The 64-bit adder has 128 inputs. Now, if you have 128 inputs, in that case, you need to apply 2 raised to the power 128 inputs to completely or thoroughly check that particular functionality of that particular circuit. So let's say that here I have a IC which has 100 inputs. In that case, I need to apply 2 raised to the power 100 inputs. Now 2 raised to the power 100 is roughly equal to 10 raised to the power 30 10 raised to the power 30 inputs that I need to apply. if I can apply one input per cycle, and your design is operating at 1 gigahertz, in that case I can apply 10 raised to the power 9 vectors per second. Now, if you apply 10 raised to the power 9 vectors per second, in that case, the total number of vectors that you need to apply is 10 raised to the power 30. That is divided by 10 raised to the power 9. That would be equal to 10 raised to the power 21. Now, 10 raised to the power 20, it will take 10 raised to the power 21 seconds to complete this process. 10 raised to the power 21 second is roughly equal to 400 billion centuries. So that means the design that you have created today would be ready for the use after 400 billion centuries, which is totally impractical. None of us will be there in this world at that point in time. So therefore, I cannot apply all possible inputs. I have to apply only a few inputs, and then the main job is to find out that which inputs I should apply, so that you can apply these test vectors in a given reasonable time. And reasonable time here, I have already explained you that it is few seconds to few minutes. Now within that, you can check that how many inputs I can apply. So now, as I said in the even couple of minutes ago, that the in practice the test is more concerned about the high end circuits which have lower yield. Say if yield is very high, say for example, the yield is something 100%. That means no device is failing. That means even if I don't test and send it to the market, no, I mean all device will work, because my yield is very high. If I say my yield is 99%, that means out of 100 devices, one device may fail, rest of the devices may will work correctly. So if the yield is very high, I don't need to identify or don't need to be so much worried about that. But if yield is low, in that case we have to be worried about it. So now so now few seconds of the test time on very expensive production testers that we need to have. Many of so within this say few seconds to few minutes time, what you can do is you can apply several thousands of input patterns. So that is the kind of input patterns that you have to find out of 10 raised to the power 30 or something like those patterns. Now, which thousands of the patterns we should choose to apply to test the device, that's the main concern here we have. So therefore, this test pattern must be carefully chosen to uncover the defects that may likely to occur in the manufactured chip. It has high economic impact. So test costs are approach. I mean, as we discussed that it is already approaching or approached near to the total design and manufacturing cost. So this, say one example I give you, that how good my test should be. Let's say that here I want to design a system, and that system uh, has something like 100 chips, and I want to accept any system that can have 1% defect. So 1% defect means one system out of 100 system may go bad, others should be good. Now, so in order to ascertain that, what I need, because 100 systems, uh, 1% means here one system out of 100 systems can go bad. Now 100 systems will have how many chips? If one system has 100 chips, in that case we can have 10,000 chips in 100 systems. Now if any of 10,000 chips goes bad, the one of the systems will go bad. So that means here one defective chips can bring in 1% defect rate. So now this will say that I can afford to sell one defective parts per 10,000 parts that I'm manufacturing. In other word, I can say that if I manufacture 1 million parts, in that case I can afford to send or ship 100 defective parts. So that number we call as DPPM, defective parts per million manufactured parts that we have. So maybe in this case, if I can say that I want I can tolerate 1% defect rate, in that case perhaps my aim is to have 100 defective parts per million manufactured parts. So this requirement varies from application to application. If it is say like here the normal ASICs that we are using for audio, visual, such kind of applications, then perhaps the tolerable defective parts per million manufactured parts is can go to 100. Now if it is some kind of like the IC that is being used in automotive, in that case ideally we want zero defect. That means here it should not have any defect at all. uh, but but we cannot ensure that this cannot have at all any defect, but the defect level per say manufactured million parts we can have is something like should be in single digit. So that means somewhere less than 10 defective parts per million parts we can accept if you want to use that part for the automotive applications. Now let's say that here I assume that I'm manufacturing 2 million ICs and IC yield is 50%. 50% means 50% chips are good, 50% chips are bad. That means out of 2 million chips, 1 million chips are good, 1 million chips are bad. Now I'm not worried about the good chips. Even if I don't test those chips will do well in the market. However, out of this 1 million bad chips that I have manufactured, what I want that because my DPPM requirement is 100, so that means I cannot afford to have more than 100 bad devices to be shipped in the market. Now 100 bad devices out of uh, the shipped devices that we have. So that means my test should uncover or can identify 9 lakhs 999,900 chips as good chips and 100 chips as bad chips. So all these are out of say 1 million parts. So that means this can ensure the DPPM as 100, and this also gives me the test coverage that how many coverage uh, defect I can cover, and that number has to be 99.99 percentage. So you divide this number by say 10,000 and you will get 99.99%. So now here maybe can I use 10 more minutes?
Yes, sir. Yes, sir.
Sure, sure.
Okay. So sorry, I'm overrunning, but there is little part that if I can cover, then maybe rest of the things can be built upon that. Now for testing, so what for we are testing? We are testing for the manufacturing defects. Manufacturing defects are almost
Perfectly okay.
okay. Thank you, sir. So manufacturing defects are of two types. One we call as a gross defects, another one is random defects. Gross defects are coming in the chips which are designed with mostly the latest technology, wherein the processes have not been thoroughly characterized yet. So, like for example, today if we are manufacturing 3 nanometer chips, in that case, those technologies have not been modeled properly, and then because of that, the devices which we are manufacturing, perhaps if there is the defect in one device, perhaps that kind of defect may run in all kind of devices. So those are the systematic defects or gross defects that we can have. Another one is the random defects. Random defects are the defects which are like a on and off occurring because of some other issues, like for example, when you are manufacturing, if some dust particle is there in the environment and that sits wherever you are laying down the wire, it may create the discontinuity in the wire, and those are the random defects. So generally the older technology will have random defects, whereas the newer technology can have random defects as well as the systematic defects. Now, so in matured and when well controlled process, the die yield is mostly limited by the random defect. However, in the say immatured process, that the yield is dependent on the systematic defect or gross defect. Now, say one can model. I mean, this is empirical model that we can have. That if I make a die, and it's very important point here one has to understand, that I make a die, and die so that means this die I have to manufacture over a wafer. Now wafer is large size. Today we can process 12-inch dia wafer. So 12-inch dia wafer can have large number of chips. Maybe single chip can have say die size maybe can have 400, 500 to thousands of the dies. Now the yield of this is modeled as e raised to the power minus lambda, where the lambda is the number of defects that we can get per die. So now say if the defects are randomly distributed, in that case, now those defects are say you can have it is scattered. Like in this particular die, you can see that uh, uh, there are I mean every defect is in new die, and therefore you all those dies wherever there are say crosses, those are bad dies and others are good dies. So now over the years in the design cycle, what has not changed, and that is really strange, that the defect density means the number of defects we can get per square centimeter, that has not changed over the years. Though we are making we are processing the larger and larger wafers, and manufacturing large size circuits, so that the defect density is varying somewhere from zero point 0.2 to 1 defect per centimeter square, or zero point 0.2 defects per square centimeter. So now the total the average number of defects would be defect density multiplied by the die area. So if say there is one defect per centimeter square and my die area is say 100 centimeter square, in that case there would be 100 defects that we may get. If there is a zero point 0.2 defects per centimeter square and there are 100 centimeter square die area, in that case you will get only only 20 defective dies, and other dies would be good. So now because this defect density remained almost constant over the years, therefore the yield you can say is e raised to the power minus lambda. And in worst case, if you say del lambda is equal to 1, in that case the yield would be 1 by e. 1 by e means here it is almost like a 37%. That's very bad. Scenario is not that bad either. Because the defects in general, defects are not, they not randomly distributed, but they are somehow clustered. If they are clustered in that case, you may not get that many bad dies out of it. Now this kind of yield perhaps put the more say pressure on how good we are in testing. Let's say that my test can cover 99.99% defects that can happen, or faults that can happen on my chip. That means there can be 100 bad devices, 100 devices can escape, or you can have 100 defective parts per million manufacturing parts that I can have, because I can afford to have 0.01 percentage devices as bad. So if I say that I have 1 million parts and my yield is 10%, in that case 1 lakh chips are bad and 9 lakh chips are good, right? Sorry, 1 lakh chips are good and 9 lakh chips are bad, because my yield is 10%. Good chips anyway we are shipping, but out of this 9 lakhs bad chips, what we get is 90, because my DPPM is the test coverage is 99.99%. So that means 99.99% chips we can identify correctly, but then 0.01% chips we cannot identify correctly. Those are incorrectly classified as good chips, and therefore out of 9 lakhs I can get 90 chips, bad chips, that we can ship to the customer. Now 90 bad chips out of 1 million good chips that we are shipping. So we are shipping 1 million good chips as well as 90 bad chips. 90 bad chips with out of 1 million good chips result into 900. So that we gives me now 900 DPPM, defective parts per million manufactured parts that we have. On the contrary, if my yield is 90%, means that my out of my 1 million manufactured parts, 9 lakhs chips are good and 1 lakh chips are bad. 9 lakh good chips we are shipping, but the 1 million bad parts, because of 99.99 percentage coverage, we can get the 10 chips which can escape out of this process, and therefore I am shipping 9 lakhs plus 10 chips. Now this 10 chips are the defective chips, 9 chips, roughly 9 lakh chips are good chips, and therefore now my defective parts per million shipped parts would be 10 divided by 0.09, and that would uh, be 11. So that means if my yield is very high, in that case my DPPM will reduce to 11. So that means if my yield is very high, and if I'm looking for DPPM 10 or something like that, in that case I'm fine to have test coverage 99.99%. So that means if I can cover the 99.99 percent model faults, I'm fine with that. Now, as I said that here the problem is testing the large dice. I can skip, this is not important. So important thing is that now when I'm testing, I'm applying some test stimuli to this, and then can check the output where and now the output of the chip my tester can receive and can compare whether I'm getting the right output or not. If I'm getting right output, in that case that test vector passes, otherwise that test vector fails. And if test vector fails, in that case it can tell that here this particular chip is defective chip, and then we can throw that out. So keep in mind that the aim of VLSI test is to find whether the chip is the defective chip or not. We are not interested what kind of defect that particular chip has. And to identify what kind of defect it has is called as the fault diagnosis or chip. So when we call VLSI test, means it is like a pass fail kind of test. This is one of the tester that advanced manufacture. And so you can maybe you can look at these slides, that if I buy a tester, that tester cost me some amount, I use that over the couple of years, and now when I use that for a couple of years, in that case I will spend some money on the maintenance, some money on the say operation, like running AC and having more manpower, etc. So that is some running cost, and then some fixed cost I am paying. And then if I divide that per unit time, in that case it comes out to be something like a 5 cents per second or something like that, which is really a large number. So the maybe this I can skip. So now one important thing that we can have. So in the if you look at the failure of the devices, what happens once I manufacture the devices? In that case, some devices say are good bad devices that we are likely to test during the just after manufacturing, but some devices are bad devices which are weak. Those are not bad devices at the time of manufacturing, but the defect will start to develop when it is operating, and within few weeks these chips will fail. This kind of failure of chip in we call as the infant mortality. So some of the chips do fail during the first few weeks. If the chips which can survive during that particular time, after that they can work well for 5 to 10 years, and after 10 years you start to get the wear out, and because of the wear out you will get the large say you will start to get some chips which are failing. So those are the failures are coming because of the aging of the devices. So it's not only that human is getting aged, all the electronic devices are also getting aged, although there is no physical wearing of the devices, but then they have aging impact when you are operating those particular devices, and they will fail after some time. So this is the working time span. So from after few weeks to few years, they work reasonably well. So our aim is to find out all the bad chips at the time t equal to 0 when we are manufacturing, and then they also weed out all these chips which are likely to fail in the near future. So now, as I said, that defect oriented testing is a open problem. It's not possible to target each and every defect. But what we can target is that if there is a defect, in that case, how that defect manifests itself in terms of malfunctioning of the chip, and that we call as the fault. So a defect we define as a defect is in an electronic system is the unintended difference between the implemented hardware and its intended design. So design wants to have something, and then the hardware which we are manufacturing perhaps may differ from there. Now, because of this, there may be an error in the output. So error we define as the wrong output signal produced by the defective system, we call as error. So error is an effect whose cause is some defect. Because of some defect we are getting the error at the output. Now this will, so a logical abstraction of this error we call as a fault. So a fault is the representation of a defect at the abstracted functional level. Uh, so uh, so therefore, because we cannot directly target the defect, therefore we have to model a defect in the form of a fault. Now what are the fault models? So first thing is why we need to model the faults. So because of IO functional test is not possible at all, is inadequate, because I need large number of tests, which are not possible. Real defects, which are often mechanical, too numerous, so they are large in number, and often they are not analyzable. So a fault model identifies a target for testing, that what for I am testing, and I'm coming in a minute that how I can model a fault, and then so that I can target that how to develop a test vector for a given particular fault. So fault model makes the system analyzable. That's the beauty of the fault model. Effectiveness measurable, this also tell you that how effective your test vector is. Now defects can be like numerous, like for example processing defect. That means there can be a missing contact window, can be a parasitic transistor formation, there can be oxide breakdown, there can be a defect in the material, there can be a bulk defect. That means there can be a crack, or can be crystal imperfection, there can be surfacial impurity, you can have a time dependent failure, like here as I said, that when it operates, there may be evaporation of some metal, that can result into open, so those we call as electromigration, or there can be a dielectric breakdown between the source and the channel. Or there can be packaging failure, like there can be a degradation in the contact, or you have seal that can be leaked or something like that. So now the defect can happen because, say, if there is a electromigration can take away the metal which is there at some point. So for example, this can produce an open, because some metal has been migrated from this particular place, and that migrated metal might have been made the sort between the two lines, and so while you are manufacturing, perhaps the two lines can be sorted by say by a small whisker, or two different layers can be sorted by hillock. There may be other kind of physical defects that can come, that there may be a sort of the gate and source, there can be sort of a resistance that we are manufacturing. All these kind of say defect that can come. So here it is showing the multiple kind of defect. Now these are defects are numerous. They can be at the, say, defect can appear here, that may result into so there would be a defect, this via is say sorted over here. This may be a resistive via, because this metal has to go through via, and that can be a resistive via, and because of this resistive via, this transistor may not work as a transistor it is intended to work. So their logical manifestation can be like here, because this is a NAND circuit, NOR circuit, so the output would be like here, always won't change the value of the output Z, can is always remain zero. It won't let it to charge to the VDD, and so that means I can model this particular fault like this. The net Z is always stuck to logic 0. This won't change, but that is coming because of some defect. That defect is that this via is a resistive via. So one of the model that we call as stuck at fault model, perhaps the rest of the uh, talks will build upon this. Stuck at fault model, we call this is a abstracted fault model or a logical fault model, or sometimes we call as Boolean fault model or a functional fault model. uh, or behavior, but this has nothing doing with the defect. What it does is this can give you so this is like here, for example, I have shown you that there is a defect over here, but that defect is manifest itself like here. The output Z is always connected to logic 0. Connected to logic 0 doesn't mean all the time that it is sorted to the ground line. The impact is like here, this is sorted to the ground line. So that's why we call as a stuck at fault model. Stuck at simply mean a net can stuck, and can stuck to what? In logical, it can stuck either to a logic 0 or it can stuck to logic 1. So therefore, what I can model as is that any net that I can have in my system can stuck to logic 0 or logic 1. So stuck at fault model is a functional fault model on a Boolean function that we are implementing. It is not a physical defect model. That means stuck at 1 does not imply line is sorted to VDD, or stuck at 0 does not imply that line is sorted to the ground. This is at higher level of abstraction. It is an abstract fault model. A logic stuck at 1 means when the line is applied a logic 0, it produces logical error. A logical error 0 becomes 1, or vice versa. It is independent of underlying technology that we are using, whether it's a CMOS or TTL or any other technology that we are using. Now, in order to, so every net in a say network can be either a good net, or it can stuck to logical 0, or it can stuck to logical 1. If it is stuck to logic 0, in that case, no matter how much time you give, this will always remain as logic 0. So let's say that this point 0 is G is at stuck to logic 0. That means now here this won't change from 0 to 1. Now how I would test this, whether this particular fault is there or not? What I want, if I can apply some input which can create 0 at G, is not going to change the output from which is different from the correct output that I am getting. Therefore, I need to have here the opposite value. If I have opposite value, in that case, in the fault-free circuit, it gives me some value, and if it is a faulty circuit, in that case, it will give me some value which is different from the fault-free value. And therefore, now in order to test this G stack at 1, what I want that the input of this AND gate must be 1 1. Only in that case I can produce 1 at the output. Now one of the input is connected to A, so I can directly apply from the primary input, but the another input F, that is in the middle of the circuit, and I cannot apply any arbitrary value over there. In order to apply 1 at F, what I need, I can go back and see that there is an inverter sitting behind this, and if I apply 0 at the input of this inverter, in that case it will provide me output 1 at F. But because so that means now I have to apply 0 to C. Keep in mind so now if I apply 0 to C and 1 to A, I can get 1 at G, but I cannot observe the value from G, and therefore now you have to transfer this output of the gate of G to the primary output, that is Y. And therefore now here to get at the primary output, I need to have H equal to 1, and for H equal to 1 now uh, no, H equal to 0, because if the H equal to 1, in that case output Y is always 1. So what I want this H equal to 0. H equal to 0 I can only get if C is equal to 0. At the moment C is equal to 0, H would be equal to 0, and then this fault effect that I am getting over here at the G will change to or move to Y. So now uh, so this way I can model a fault, and then can develop the test vector for a fault. Maybe a more elaborate way it would be discussed in the next couple of lectures. uh, so in I see that there can be a permanent fault that we call as hard fault, like stuck at 0 fault. A model is one which can capture that. There are another faults that we will discuss sometimes later, but they can be called as temporary fault or soft transient faults, which appear sometimes, or this can appear intermittently, which are not there all the time. So there are various fault models that people have developed. One is single stuck at fault, which is most commonly used fault model in the industry. Every industry has to test for all the single stuck at faults. Though design is a complex, and it's very difficult to believe that there can be a single stuck at fault in the entire design. The reality is that there are numerous faults, but still we are using single stuck at fault model, because the test vector that we are generating for the single stuck at fault are likely to capture the most of the multiple stuck at faults. Then there are some faults which are like a transistor open, transistor short, which are there when you have a transistor level design. There are the faults in the memory, PLA, functional fault model, or timing faults that we will discuss. Let's say that this is one circuit that is perhaps, this is typical implementation of a XOR gate. Now this XOR gate has say about 12 nets. Keep in mind that fault stuck at 0 fault, if I say, that doesn't mean that that point is connected to the ground, and therefore the fault at the stem of a fan out point, and fault at the branch of this fan out point are different faults. They are not same. There may be a fault at the stem, but that same fault may not be there at the branching points. So in this there are 12 faults, and then when I want to test, I have to target each and every fault and generate the test vector for that, and these generated test vectors have to be applied on individual circuit. So maybe I skip over here, that now if I want, if this is an AND gate, and see in this AND gate, maybe this is the last slide I'm using. I can apply the four possible inputs, 0 0 0 1 1 0 1 1, and say that the every point here, either this is a good point, that means here there is no defect at all, or there can be a fault. Fault can be stuck at 0, stuck at 1. So how many faults can be there? There are 3 nets, so therefore there can be 6 faults. Now either circuit is a fault free circuit, or it can have a stuck at 0 fault at A, or it can have stuck at 0 fault at B, or stuck at 0 fault at Z, or there can be stuck at 1 fault at A, or stuck at 1 fault at B, or stuck at 1 fault at Z. Now say if I apply 0 0 at the input, what output we are getting? 0 0 0, right? So good response is 0, but if there is a stuck at 0 fault, in that case also I am getting 0. If there is a stuck at 0 fault at B, then I am also getting 0. If there is a stuck at fault at 0 at Z, then also I am getting 0. If there is a stuck at 1 fault at A, then also I am getting 0, and stuck at 1 fault at B, then also I am getting 0. And then if Z is 1, in that case I am getting this output as 1. So now if I say apply the input 0 0, in that case it can detect only this fault. However, if I apply say 0 1, in that case it can detect these two faults, A0 and Z, I mean A1 and Z1. If I apply 1 1, in that case it can detect these three faults, A1, B1 and Z1. That means A stuck at 1, B stuck at 1, or Z stuck at 1. Now aim is to, because for every if there are n number of nets in my circuit, I can have 2n number of faults, but one vector can test multiple faults. What I want to cover all the faults with the minimum number of test vectors. So the problem is to find out the minimum number of test vectors that can cover all possible modeled fault. And here modeled faults are the stuck at faults. Stuck at faults are the faults which can occur at a net that can manifest itself as stuck at 0 or stuck at 1. With this, I say conclude this particular part of the talk, and then the rest of the sessions will build upon this. So we have discussed that why the VLSI test is important, how important it is from the industry point of view or from research point of view, and then say if I need to have testing that can uncover all the defects. However, all the defects I cannot target, and therefore we model the impact of these defects in terms of the logical malfunctioning of the circuit, and that model we called as a fault model. And very commonly used fault model is single stuck at 0 fault model. That means a particular net can be stuck to logic 0, can stuck to logic 1, or it would be a good net. And if a circuit is fault free, if your all the nets are good nets. So with this, thank you very much for your patience for listening. If you have any question, I would be happy to answer.
Thank you so much, sir, for the insightful talk. And it's really covered hopefully what is the industrial demand, how the simple from very simple to how the single stack faults are going to happen, and how these are covering the multiple stack faults, the same vector is going to cover. Sir, we have a question in the chat box. If you can take this question.
There's one question in chat box, Shankar.
चैट बॉक्स
साई कुमार
पर चैट, हाँ
चैट जो है बॉटम पे राइट से एक्सट्रीम राइट में
हाँ यस सर. If why a few second test is very expensive? If we buy a test engine, it is one time investment. right, and I listen, normal test time in industry is less than 1 millisecond. So even though one company manufacture 1 million chips to test those chips, it will take 100 seconds only. So what is the problem with the test time? So as I mentioned earlier, if I want to test comprehensively, exhaustively, in that case it takes billions of centuries. Now, because tester is expensive, it costs you billions of dollars, and that I buy a tester and I operate over few years. If I distribute that cost per unit time, then it approximately comes out as 5 to 6 rupees per second. Now, if I have if I spend 5 to 6 rupees per second, then what reason? I mean, the entire this thing is say governed by the cost. How much money I can spend on testing a device? For example, if you want to buy a microcontroller, a 8051 type of microcontroller you can buy in 60-70 rupees. Can I imagine to spend 300 400 rupees to test that particular microcontroller? Perhaps may not, because even in 70-80 rupees you can buy that microprocessor that had cost, I mean, test cost included. So therefore now I have to test that particular device less than a second. Now you have written that you can test in millisecond. There are only very small designs can be tested in millisecond, but most of the devices are I mean, consuming say seconds to the minutes. All like your high-end microprocessors are consuming minutes. But then if you go to minutes, in that case it will cost you 1,000, 2,000, 5,000 rupees. So it is how many vectors I can apply, that is governed by how much money I can afford to. And that is the say a big issue in test. So the reasonable time in testing is something like few seconds to few minutes. However, reasonable time in verification is something like a few months. If you can verify your design in 6 months, that's perfectly fine. However, it is not fine to have more than that time here.
Thank you so much, sir.
Yeah, so that is the only one question.
So,
So single stack at fault means we are assuming that at a time there is only one fault exists in the circuit. I have a circuit of billion gates, right? It is, as I said, it is not reasonable to assume that there can be only uh, one fault in the circuit. However, this fault model that was developed way back in 60s is still surviving. Industry is still using the single stack fault model, because not that we are thinking that there can be only one fault at a time, but the test vectors that we are generating using single stack fault model are capable to test 70-80% of the multiple stack faults. And therefore industry is fine to use single stack fault model and develop the test vectors which are reasonably good for multiple stack fault. The problem with multiple stack fault model is, if I can use the multiple stack fault model, then the number of multiple stack fault would be 3 raised to the power n minus 1, where n is the number of nets that I have. That if n is something like, say if I have 1 million nets in my circuit, in that case this will go to 3 raised to the power 1 million minus 1. That would be impossible to target, and therefore multiple stack faults are not doable. Hence we are using the single stack at fault model. At multiple point in time, multiple researchers have evaluated how good the test vectors that we have, which we have developed. So for large circuits, of course, you cannot test exhaustively, but for small circuits you can test exhaustively, and people have evaluated that how many multiple stacked faults the test vectors generated from a single stacked fault model are able to uncover, and that number is something like a 70-80%. And that's how the single stacked fault model is surviving.
Thank you,
In,
sir. So I
in
hope
variable
it answers
industry
your
meetings.
question, Mr. Sai Kumar. Yeah. So thank you so much, sir. It was really very insightful lecture. And now we will take the next
Okay,
lecture after
thank you.
5 minutes break.
Thank you. Thank you.
Thank you, Virendra.
Thank you, sir. So now, shall I log out?
Hi, yes, sir. Let me log out, sir. Thank you so much, sir.
Thank you. My apology for initial all these disruptions
No problem,
and
sir. There
problems.
is some technical glitch. Sometimes it happens, sir.
Hope it won't happen tomorrow. Now things are
Yes,
okay.
sir. Now it is first time is difficult, then it actually goes well.
Okay. Bye.
Yes, sir. Thank you, sir. Very nice.